Dear students, welcome to lecture 2 of heat transfer. In the last class, we looked at conduction through a flat wall. So we will quickly recap on that. And followed by that, we will look at conduction through solids in series. So it's basically flat walls in series. And with that, we will look at conduction through a hollow cylinder and hollow sphere. And finally, we will try to combine conduction and convection, which is usually a real life scenario. So to recap on what we saw in the last class, okay, so shown here in the schematic is a flat slab or wall with temperatures T1 and T2 on either sides. Let me get the laser pointer. Okay, so with temperature T1 and T2 on either sides, so you can see that temperature T1 is larger than T2, and that indicates that thermal energy at point 1 is higher than point 2, and we know that energy flows from point of high energy to low energy, so therefore heat transfer occurs from 1 to 2, right? So which is represented by Q. This is rate of heat transfer. Q is rate of heat transfer. And we also discussed that this is a steady state scenario wherein T1, T2, and Q, they don't change with time. All right. So this is a steady state. Okay. So things don't change with time. All right. And we started from Fourier's law, and we integrated it on either sides, and we ended up with this form over here. All right. So T1 minus T2, that is your driving force. T1 minus T2 is your driving force, and this form actually can be rearranged such that you can have rate is equal to driving force by resistance. We will look at that later. Okay, so in this slide we don't have the resistance form, but in a later slide we will rearrange it in that fashion. All right. So that is similar to I is equal to V by R that you would see in electricity. All right. I is current. Okay. So which is equal to voltage by resistance. All right. So here you have a Q that is analogous to a current, and your T1 minus T2, your driving force, which is analogous to the voltage divided by resistance. Okay, so that way you can remember this formula as well. Okay, so it's very similar to V is equal to IR, right? So this is a very simple case for heat transfer via conduction. And now let's move on to conduction through plane walls in series. All right. So this, for example, you can think about your wall. Okay, so in buildings where we have layers of insulation. Okay, so it can be a concrete and some insulation, and then some a plaster, right? So they all have their own thermal conductivity. We have seen that thermal conductivity is property of material. All right, so here we are looking at plane walls in series. So we have three materials A, B, and C in series, which so A, B, and C in series, which are of a thickness as mentioned here, and temperatures on either side of the material is also indicated here. All right, and still we are looking at a steady state scenario, and because of which rate of heat transfer across material A will be equal to material B, which will be equal to C. All right, so the rate of heat transfer remains the same throughout. Okay, so you can call it as QA, QB, QC, which would be equal to Q. All right, so rate of heat transfer is the same across. All right, so it doesn't change with time. All right, So let's see how this rate of heat transfer form would look like. Okay, so we would start with what we derived for a single wall case. Okay, so Q is equal to, for material A, this is the form. Okay, so if you go back to your single wall scenario, okay, so this is the form for material A, which we just saw that, if you call this as QA, this would be equal to QB, all right, and which again will be equal to QC, all right. So the above equation can be rearranged to the equation shown over here. Okay, so you have T1 minus T2 on one side, all right, and you take this whole term to the other side, basically, all right. So you rearrange it and you get three equations. Okay, now let's sum up all these three equations. Then what would happen is, okay, so minus t2 plus t2 would get cancelled, minus t3 plus t3 would get cancelled, and you would end up having t1 minus t4, all right, and all these other terms that go into the denominator, all right. So now what you see is you have t1 minus t4. Okay, so when you go back to your schematic, you see that t1 and t4 are on either side of this multi-layer wall. Okay, so this is the overall driving force. Okay, so basically the overall driving force comes at the numerator, and what we have in the denominator, like what we saw for the single wall scenario, is the resistance. Okay, but in this case it's summation of resistance. Okay, so now you can see the form for resistance actually. Okay, so the resistance is equal to delta x by Ka. All right, so this is the form for the resistance basically. And so for plain wall in series, the rate of heat transfer form is basically overall driving force by summation of all the resistances. Okay, and you can see that how this term is somewhat similar to a resistance. Okay, so if okay, so your thermal conductivity is very high, right? So then heat transfer happens fast. Okay, so which means that resistance is low, all right. And now you see that in this resistance term, thermal conductivity is in the denominator, right? So when thermal conductivity goes high, resistance comes down, so which makes sense, right? And likewise when you look at your delta x, okay, so as you increase delta x, resistance is supposed to increase, right? As you keep on adding more layer, then you are adding more resistance to heat transfer. Okay, so that's what you see mathematically as well. Okay, so you can infer it that way too. Okay, and just to recap this area, so there are several ways you can calculate area in this plane wall, but we are looking at the area that is normal to the direction of heat transfer. All right, so let's say let me try to get the shading screen. Okay, so yeah, you can calculate A here, but this is not normal to the direction of heat transfer. Or you can calculate A here, but this is also not normal to the direction of heat transfer. Okay, so we are looking at this area. All right, so that's what you should always remember. Okay, so Q is flowing in this direction, and we are looking at the area normal to the direction of heat transfer. I'm trying to clear out this drawing before proceeding further. All right. Okay. So I hope everyone is clear with this form now. So now let's look at a problem to see how this mathematical form can be applied. All right. So here is a scenario. A cold storage room is constructed of an inner layer of 12.7 mm of pine. Okay, so another board. Okay, so which is this millimeter thick, and a third layer which is about this millimeter thick. All right. So thickness for A, B, C are given, and the wall surface temperature on one side it is given. All right, and on the other side, okay, so which is 297, okay, so which is also given. All right, so if you are smart enough, you should have noticed that, okay, so unlike what is shown in the schematic where T1 is larger than T4, right, only then heat energy will flow from 1 to 4, right? But unlike that case, in this case, okay, so the temperature corresponding to T1 is lower than T4. So if you have noticed that, that's a very good smart observation. All right, so yes, that is true. Okay, but let's keep that aside and still solve this problem as we have derived, and look at the result. Okay, and try to analyze the scenario based upon the result we get. All right. Okay, and the thermal conductivity for all these three materials are also provided here. All right, so remember the units for thermal conductivity is watt per meter Kelvin. Okay, and you are asked to calculate heat loss. Okay, so that is rate of heat transfer. Okay, so when we talk about watt, it is joule per second. Okay, so and when we talk about rate, it is always per second, right? Okay, so rate. All right, and for 1 meter square. Okay, so area is given as 1 meter square. Okay, so this area we are talking about has been provided. Okay, and not only that, okay, so they are asking you to calculate Q. So they are also asking you to calculate one of the temperatures in between. All right, okay, so let's say pine, corkboard, and concrete, right? So they are asking to calculate the temperature at the interface of wood and cardboard. Okay, so this is pine and cardboard. Okay, so they are asking you to calculate T2 as well. Okay, so let's do one at a time. Okay, so our first goal is to calculate Q. All right, okay, so this is the formula that I will be using, and everything is given, right? What you see in this formula, everything is given. Okay, so you just have to calculate one term at a time. All right, so we have listed all the givens over here, and now you calculate the resistances. Okay, so you calculate the resistances. Okay, so all the three resistance, and now apply, substitute them into the bigger form to calculate Q. All right, and what is interesting that you see here. Okay, so Q takes a negative sign. All right, so this is what we spoke at the beginning, that T1, as opposed to what you would see in the schematic, is lower than T4. All right, and the negative sign indicates that heat is not flowing from 1 to 4 for this case, but is flowing in the opposite direction. All right, so that's what the negative sign here indicates. Hope that makes sense, right? Okay, and for the other case, okay, so you have calculated the Q, right? And which would be equal to QA. We have was seen that before, right? This is at a steady state. Q is equal to QA is equal to QB is equal to QC, and within this QA form, everything else except T2 is known. Okay, so you basically go and substitute everything that you know, and from there you can calculate T2. All right. All right, let's move on to, okay, so we looked at conduction through flat wall, a single wall, and we expanded it to multi-layer wall or walls in series. Now we'll look at how the form will look like for conduction through a hollow cylinder. All right. Okay. So we start with the Fourier's form. Okay. Or let me explain the schematic before. All right. Okay, so we are talking about the hollow cylinder over here, and the hollow cylinder is very important in industries because fluids are being transferred from one point to the other in cylinders. And not only that, when we look at the heat exchangers, so it's basically a lot of pipes, that are placed in unit which transfer heat from one fluid to other. All right, so hollow cylinder is very important in chemical industry. And shown over here is a hollow cylinder with inner radius R1 and outer radius R2. All right, so owing to temperature difference at 1 and 2, and usually we know that, okay, so if T1 is larger than T2, then heat will flow from in to out, right? So Q is Q will flow in this direction as shown over here. And okay, so in the slide we would want to derive a mathematical form for Q. All right, and what is different compared to your flat wall case is that in a flat wall case, in the direction or the area normal to the direction of heat transfer was constant there. Okay, so it did not change. Okay, however, for this case, as you move further and further, then the area changes. Okay, so the area keeps on increasing. All right, so a is also a variable. Okay, so with change in r, okay, so a also changes, right? And to be clear to you guys, okay, so the area that is normal to the direction of heat transfer is this in the schematic. All right, yes, okay, so it should be equal to what? 2 pi r L. All right, 2 pi r and then multiplied by L. That is your area normal to the direction of heat transfer. And as we move from the inside layer to the outside layer, or changes, right? So this area also changes. Okay. All right, okay. But from there, everything else is similar to what you have seen before. Okay, so you substitute area in this Fourier's form, and you integrate from point 1 to point 2. Now r is also a variable, so that's within the integral. And from there, you end up with this final form. Okay, and this form you can apply to calculate rate of heat transfer through a hollow cylinder. Okay, all right, and you can very well apply the previous form, but if you would want to rearrange it in a manner similar to what we saw for the flat wall case, where we had Q is equal to driving force by resistance, we do this rearrangement basically. Okay, so we define what is called as an log mean area. ALM stands for log mean area. Okay, so area for outside minus area by inside. Okay, divided by ln of A out by A in. Okay, so you define this, and you basically substitute, okay, ln m logarithmic mean area, okay, so this form into 1. Okay, so into this equation. Okay, so you can try to substitute it out. All right, and you will end up with this form over here. All right. So you will end up with this form where you can call R2 minus R1 by KALM as the resistance. Okay, so that's similar to what you saw before. Okay, so in the flat wall case, it was delta X by KA. Here you have delta R by KALM. All right, log mean area is this area. Okay, so you're utilizing a log mean area because area changes from 1 to 2. All right, so you take a mean and you use that area. Okay, so with that case, okay, so you get a q which is similar to the previous form, t1 minus t2 by r. All right, so where resistance is this actually. Okay, and if in case your a2 by a1 is less than 1.5, so which means that the area doesn't change much. In that case, your log mean area will be approximately equal to arithmetic mean area. Okay, so instead of calculating log mean area, you can simply use an arithmetic mean area in that case. Okay, so that's what this line is stating. All right, so you have two forms. Okay, so for q for a hollow cylinder, okay, so either the one that's shown over here at the top, or you can use this one. Okay, so whichever is appropriate to the problem statement, you could use that. All right, and next we have conduction through a hollow sphere. So there are example problems for conduction through a hollow cylinder if you take a look at the book. Okay, but we are skipping it here, and we will move on to conduction through a hollow sphere. And it's again pretty much similar to the previous derivations. Okay, so we start with the Fourier's form, and in this case a is equal to 4 pi r square. All right, and yes, we saw for the case of a cylinder. Okay, so r changes and therefore a changes as well. Okay, so r is a variable here. Okay, so that's different from what you saw for a plane wall. Okay, and so hollow spheres are have importance in industries as a storage vessel. Okay, so when you look at a hollow sphere, unlike a cylindrical vessel where there is a sudden change, okay, so from one shape to the other, so you will have points of weakness, but in a hollow sphere it seamlessly moves around, and the pressure is distributed equally throughout, and therefore you won't have points of weakness. Okay, and so when you want to store fluids that can lead to a high pressure and damage the vessel, in such scenarios hollow spheres are preferred. All right, and so now let's getting back to the derivation, which is pretty much similar. You substitute this area into this Fourier's form we have seen before, and you integrate it from point 1 to point 2, and you end up with this form. Okay, not quite like the delta t by resistance that we have seen before, but for the hollow cylinder case, we did some modifications, and we ended up with that form. But for the hollow sphere case, okay, just this. Okay, so we cannot do any modifications beyond this. Okay, so this is what it is. All right. Okay, and there should be a problem statement in your book as well. So if you are interested, take a look at that. All right. So this is a summary for how a Q would look like for your plane wall, cylinder, and a sphere. Okay, so take a look at that, and you can try to compare how the form looks like for the different cases. Okay, and just to note again, for the cylinder case, we have a different form that would be analogous to what we saw for the plane wall. Okay, so you could scribble that down as well. Okay, and having seen flat walls in series. Now we will move on to cylinders in series. Okay, so this is an important scenario in industries as well. Okay, so we spoke about okay, so cylinders or pipes being used to carry fluids from one unit within a process industry to another unit. Okay, and for example, steam. Okay, so steam is distributed throughout your process plant using pipes, and of course, you don't want heat loss to occur, right? You don't want heat loss to occur. So steam is a heating agent in industries, and you don't want thermal energy to be lost as we move from point one to or as we move from one utility section to another main plant and so on. Okay, so what we do is we add insulation layer. For example, okay, so your A could be your metallic pipe where it's carrying a steam, and on top of which you add a layer of insulation, and on top of which you add another layer to hold the insulation together. All right, so that's a typical example. All right, and again, we are still looking at a steady state scenario. So therefore, all these temperatures you see, they won't change with time. Okay, and if we assume that T1 is greater than T4, then rate of heat transfer will happen from inside to outside. All right. Okay, so let's move to the derivation. So what the derivation is pretty similar to what you saw for the flat walls in series case, and this is where having the log mean area form becomes makes the derivation simpler. All right. So as we saw for the flat walls in series, Q is equal to QA is equal to QB is equal to QC, and where the log mean area for each material has been defined. Okay, so notice that. Okay, so the log mean area for A is its outside area minus its inside area divided by A2 by A1. Okay, and when we look at B, so you have to see that. Okay, now A2, which was outside area for A, becomes the inside area for B. All right, so we use these forms. Okay, so you have log mean area for A, B, and C. All right, and you could rearrange this as we saw for the flat wall case to have three equations where you have T1 minus T2 on one side, or delta T's on one side, basically, right? Three different equations. You sum them up together, then you will end up seeing that T2 gets cancelled, T3 gets cancelled, and you will have T1 minus T4, and what you see in the denominator would be similar to what you saw for flat walls in series case, having RA plus RB plus RC. All right, so pretty similar to what you saw for flat walls in series. Q is equal to your overall driving force by summation of resistances. All right, and this again in a steady state scenario. So this Q is equal to QA is equal to QB is equal to QC. All right, so you have to remember that. Okay, so a Q is same throughout. All right, so you have to remember that. All right, so let's look at a problem. Okay, so I wouldn't spend too much time on this. Okay, so it's pretty similar to the solving steps, or pretty similar to what we saw for flat walls in series, but we can quickly read if anything different is here. All right, so a thick walled tube of stainless steel. Okay, I'm waiting for, yeah, with thermal conductivity with dimensions inside and outside. Okay, so let's say if this is material A, its inside and outside is given. Okay, so you have an insulation whose thermal conductivity is given, and The inside wall temperature is given and the outside is given as well. All right. Okay. So length of the pipe is given. Okay. And calculate the heat loss. All right. Okay. So the inside wall temperature 811 and the outside. Okay. So 310. You can see that, how insulation is helping here. All right. So although it's a stainless steel that is carrying it, which is having a high thermal conductivity, right? Okay. So it has a 21 watt per meter Kelvin, whereas your insulation with a lower thermal conductivity offers high resistance, and because of which there is a temperature drop right from 811 to 310. Okay, so as a chemical engineer, as you guys are being trained as chemical engineers, you should see these practical things. Okay, so insulation is offering what it is supposed to do, insulating. All right, insulating the heat. Okay, so therefore heat loss is being maintained very minimally. All right. Okay, and okay, so everything else is pretty similar. Okay, so your T1, T3 is given. Okay, so they're asking you to find out. Okay, so as you've seen before, they are asking you to find out, the temperature at the interface. Okay, so the one over here. All right. So you would first find out Q, the overall rate of heat transfer, and you would equate it to either, QA or QB because T2 is present in either. All right, so you can do that and solve for T2. Okay, so so unlike the flat wall case, you have to before calculating resistance, you have to calculate the different areas and then the log mean area and so on. That's the only change. All right, so you spent some time calculating the log mean area. Followed by that, you calculate your resistances and calculate your rate of heat transfer in watt. Okay, joule per second again. Okay, and you equated this to one of your Q formulas, QA or QB. So in this case, they are equating it to QA, and solving which you get T2. All right. And again you can see that, you can observe that from 811. Okay, so there is only a small temperature difference. Okay, so because heat is being conducted fast. Okay, so it's pretty hot. Okay, so compared to inside. Okay, and from this 800, okay, so your insulation is doing its job, and therefore from this 800 it falls to 310 outside. Okay, so insulation is offering a huge resistance. Okay, so because your steel pipe is not offering that much of resistance. Okay, so because if its thermal conductivity is very high. Okay, and therefore the resistance is low, the temperature is being maintained about the same. Okay, so that's the quick observation you have to make. Okay, practical, you connect what you see here with the practical scenario. All right. Okay, now let's move on to the convection for rate of heat transfer via convection. Okay, so we have seen conduction where heat is being transferred from one point to the other. A medium is involved, but this medium by itself doesn't move. Okay, so this medium actually vibrates. Your molecules or your atoms or your electrons vibrates, and therefore they transfer energy from point 1 to point 2. All right, so unlike the case of conduction, so in a convection case, your medium moves. Okay, so it carries the heat from one point to the other. We have seen examples before. Okay, so one such is captured in this schematic over here. You have a hot material, a temperature TW. So it could be your hot pipe, for example, right? And as fluids, your atmospheric air blows over it, it carries the heat, right? It carries the heat away. Okay, and so And for this case, the rate of heat transfer from the metal surface to the fluid is given by this Newton's law of cooling, which is equal to HA TW minus TF. All right. So where H is your heat transfer coefficient. Okay. So this kind of dictates how fast heat is being convected. Okay, let me get to it a little later, but it's unit. Okay, so observe its unit. It's a kind of closer to your thermal conductivity unit, but here instead of watt per meter, you have watt per meter square Kelvin. Okay, so heat transfer coefficient as the unit of watts per meter square Kelvin. And you have the area, the surface area from which heat is being convected, okay, from your solid material to the fluid. Okay, so that's the area you have to consider. All right. And the driving force, okay, so your wall temperature, which is hot, and minus your fluid temperature. Okay, so that's what you would be using. And let's come back to H. So unlike the thermal conductivity case, where thermal conductivity is property of the material alone, H depends on several things. Okay, so H depends upon the fluid properties as well as, okay, so we have seen that, the fluid can flow naturally or it can be forced as well, right? So then it also depends upon the fluid dynamic properties as well. Okay, so how fast it is flowing, etc., viscosity, all of those things. Okay, and not only that, your H also depends upon the geometry of the material as well. Okay, so it also depends upon, okay, so if the fluid is flowing on top of a pipe or on top of a plate, all of those things. Okay, so H captures all of those. Okay, but what it indicates is if H is larger, as we see for, conduction. Okay, so if H is larger, convection is going to be fast. Rate of heat transfer via convection is fast. And if H comes down, and the rate of heat transfer comes down. Okay, so that makes sense. But just remember that it depends upon a lot of other things beyond just the fluid properties alone. All right. And these are examples for free or forced, which we have seen previously. Okay, and now let's try to combine both conduction and convection, which is actually a real world scenario. All right, and let's consider this flat wall here. Okay, so and it's similar to say, for example, your flat wall at home. Okay, and on a hot day, okay, so Arizona is a very good example. Okay, so on a hot day, your outside temperature T1 is larger than your inside temperature T4. Okay, so therefore heat is being transferred from outside to inside. And in this case, okay, so from the outside bulk to the outside layer of the wall, heat transfer happens via convection, right? So it's a fluid. Okay, so heat transfer happens via convection. And within the wall, although you can think about making it complicated and have flat walls in series, but to begin with, we have made it simple here. Just one material through which heat is being transferred via conduction. And from your room, within your room, from one side of this wall at 3.3 to inside your room, heat is being transferred via convection. Okay, and the we have yeah, the I has the notation has been flipped. We spoke that this is outside, this is inside, but in this case, for the scenarios, assume this has to be inside. So you have a heat transfer coefficient HI, and you have a H naught, and probably you will have a Ka for this. Okay, And similarly for your cylinder, you could also have your pipe is carrying steam, okay, but you have outside air, okay, so through which heat is being convected to, okay, and the heat is being convected from within the fluid within the pipe to the pipe, okay, so you have a combined conduction and a convection in these scenarios, okay. And how do you solve for Q? Pretty much similar to what we saw for the previous cases, okay, so in your plane wall and series case where q is equal to qa is equal to qb is equal to qc. Similarly, q is equal to heat transfer via convection within the inside fluid is equal to heat transfer via conduction within the material A is equal to heat transfer via convection within the outside fluid. Okay, so you rearrange it to get three equations in the form of different delta t's. You sum them up all together and you end up with this form. All right. And now, okay, so you can see here, this form is analogous to what we have seen before, which is equal to delta T, your overall driving force, by summation of all the resistances. Okay, so your conductivity resistance you have seen before, or conduction resistance you have seen before. Your convection resistance is 1 by HA. Okay, so this is something new that you are looking at. Okay, so this is one form, and we would want to rearrange this to a form that is similar to what we saw for convection. Okay, so that okay, so as we saw that heat transfer coefficient depends on several properties, you want to introduce, okay, so an overall heat transfer coefficient. It combines all the properties that are involved for convection as well as conduction within. Okay, so you'd want to derive this form, and for that reason what you do is, let me get the pencil. Okay, yeah, all right, so what you are going to do is multiply this, okay, so by area. Okay, so you have area and divide that by the same area, right, which means that you're multiplying by 1. Okay, so that's totally fine, right? And now what you do is this sigma r by a, or 1 by sigma r by a, basically. All right, so you call that as u, okay, the overall heat transfer coefficient. Okay, so 1 by a sigma r by a, that's what you have here. All right, so this is your sigma r, and you multiply by a, then a cancels out, there is no a here, and likewise a cancels out, a cancels out, you don't see a here. Okay, so this is u. All right, and a at the numerator here remains. Okay, so you get this form of ua delta t overall. Okay, so two different forms you can either use. Okay, so okay, and this u is called as overall heat transfer coefficient. Okay, so since this form is similar to Newton's law of cooling, where we had the heat transfer coefficient, so this variable u takes the form of, or is known as overall heat transfer coefficient. All right, so let me clear all of these. Okay. All right. So we saw combined conduction and convection for the case of a plane wall. For the case of a cylindrical wall as well, it is pretty similar. You do the derivation as previously. You write it down for QA, QB, and QC, and rearrange it so that you have delta T's on one end. You sum them up, then you will end up with this form. All right. And now, again, I want to rearrange it so that I get this UA delta T form. But now here, this is the puzzle. Okay, so in the case of plane wall case, we know that the area normal to the direction of heat transfer doesn't change. But what's happening to the cylindrical wall case? Okay, so if I consider, just one material in the pipe, okay, so you have two areas, okay, an inside area and an outside area, right? So now, which area should I multiply the resistance with? That question comes, right? And so because of that, okay, so what we have is two different forms. Okay, so you have UI AI delta T or U naught A naught delta T. So basically, if you multiply and divide this form by AI AI, you get your inside overall heat transfer coefficient, which is this form. Or if you multiply and divide by A naught, you get your outside overall heat transfer coefficient, which is this form. All right, that's it. Okay. And again, it overall tells, how fast heat is being transferred from one point to the other. And so we call it as, the heat transfer coefficient. All right. So there is a problem as well. So pretty similar to what you have seen before, just that now you would have both a fluid and a pipe as well. So we can quickly go over it. So you can connect what you are learning to real life scenarios. So in this case, as I have told before, steam is flowing inside a pipe. Okay, so with both these diameters, and a pipe is insulated. Okay, so with 1.5-inch insulation. All right. So based upon the insulation thickness and the outer diameter, you should be able to calculate the outer diameter for the insulation, right? The convective coefficient HI inside is given. Convective coefficient H naught is also given, all right. And you can try to connect with what you will see in real life. Okay, so HI is much larger than H naught. Okay, so because the fluid is flowing inside, right? Okay, so its heat transfer coefficient is going to be larger than what is outside. Okay, so in outside usually it's going to be atmospheric air. Okay, so at times it blows, all right, otherwise it's usually stagnant. Okay, so therefore it's not very high. And in this case, okay, so beyond other things, okay, so your steam is pretty hot as well. Okay, so it's flowing at very high velocity. All of those things contribute to a very high heat transfer coefficient. All right. And on top of which the thermal conductivity of the both the materials are given. Okay, so calculate heat loss Q. All right. So like we have seen before, you calculate your log mean areas, and followed by that calculate your resistances, then calculate your Qs. Okay. Okay, so areas being calculated, log mean area, resistance, and finally your Q is being calculated over here. All right, so that's one. And let's see what is okay. So part B is basically a repeat Q, but now calculate overall heat transfer coefficient. All right, so you have calculated everything. Okay, so if you have calculated your sigma R, multiply that by AI, you get your overall heat transfer coefficient. Now calculate Q again. Okay, so whatever approach you take, your Q should remain the same. That's what you are seeing here. Okay, so with this, let's end lecture 2. And here, we have quickly advanced from, conduction you saw in the first class to combined conduction and convection. And in the third lecture of heat transfer, we will try to cover a few different topics to wrap up heat transfer. All right. So thank you all. See you in the next class.